In this video, we'll go through the penetrating power of alpha, beta, and gamma emission. Before we go to the questions, let's recap on the relative penetrating ability of each of them, and you kind of need to memorize them so that it will help you to know what kind of emission is used for what kind of application. Now let's start with the alpha particles, which is a helium nucleus. The penetrating is the power is the least, and it can be blocked by a piece of paper, a thin aluminum foil, even your human skin, or even a few cms of air. Okay, take note of that. And beta, which is electrons, which is very small, the penetrating power is medium, and it can be absorbed by a few thick of aluminium. So if it's a few cm of aluminium, it will be blocked totally. All right. And for gamma, it's the most penetrating, and it can pass through most material easily. It can only be stopped by maybe a few cm thick of lead, okay, or very thick concrete, maybe in terms of meters. So one way to help you to remember easily is, since alpha particle is a helium nucleus, which is the biggest, so that will give you a hint that the penetrating power will be the least. So at least the order you can remember in this way. And beta is always in the middle, so gamma on the opposite side will have the most penetrating power. Now let's go through the first question here. So the background count due to the cosmic ray natural form kind of radioactive material underground or near you is already 25 counts per minute. And when you put the radioactive source directly in front, okay, total will be 630 counts per minute. Now take note that this 630 is the count from the radioactive source plus the background radiation. And when you put a paper absorber in between the source and the detector, so the count rate remains the same. That means to say, anyway, remember, alpha particles will be absorbed by the paper. Since there's no change, no drop in the count per minute, that means to say there's an absence of alpha particle. So there's no alpha particle. And next, if you take a look at, if it's a aluminum absorber in between the source and the detector, 3 thick, okay, and the count rate will goes to 180. So remember, just now we say that a few of aluminum can absorb the beta particle. So beta particle must be present because there's a drop. Then finally, because there's still 180, much higher than the background radiation, this means to say there's a gamma emission there. So both beta and gamma rays are present. So the answer is B. Next, X, Y, Z, there are three types of radiation. Now let's look at X here. Almost completely absorbed by 5 cm lead, okay, but not by 5 of aluminium. You can refer back. Okay, so if absorbed by a lead here, only by lead, but not aluminium cannot block them. So that means this has to be your gamma rays. Okay, gamma, that's the symbol. And if Y is almost completely absorbed by 5 of aluminium, but not by a thin cut, that means they can just pass through the thin cut easily, but being absorbed by the aluminium, that means that is your beta particles. And lastly, Z here is absorbed by a thin cut, okay, that has to be your alpha particles. All right, so the answer will be D. In this question, you have different radioactive sources and you have different barriers, and you will have the different count rate that's recorded. So they ask you which source emits alpha particles only. If you can recall, alpha particles is the least penetrating, and it can be stopped by a few cm of air, by your human skin or a piece of paper or a thin aluminum foil. So having said that, so when there's no barrier, so let's say A, so after putting a paper in between, the count is still the same. That means to say there's no alpha particles present. If not, the value here should drop. So this is possible, and D is wrong already. So, and then Now, if you look at B, so even if you put aluminum and lead or paper here, it's all 30. Now, this should give you a hint that the 30 counts per minute or whatever units they are measuring. That is the background radiation. Okay, background radiation that's always there. Or you can take a look here, that will give you a hint that's background radiation. So, after passing through a paper, subsequently, whatever barrier is there, so total is all blocked. That means to say this source only have beta, because once you put a paper, it reduces to 30 background and always 30. So B will be the answer. All right. Let's go through C also. So there's a decrease in the count rate. So that means there is a alpha particle that's present, but then after you put a thin aluminium, it reduced to 200. That means to say there's beta particles that's involved. And finally, if you put a thick lead, there's a blockage of the gamma rays, then it's only the background radiation. So C, the source will have all three types of emission. So that will not be the answer. In this question, the application is to check whether the paint pigment is mixed well in a tank. That means you have a tank, you make the paint. Then after you take sample from this point, this position here, and the paint here and here, and you put it inside a steel container, the sample here, and the detector is placed 30 cm, which is constant always. So if the sample from all various positions all give the same count rate, that means to say the paint is mixed well. So, and because it's a thick steel and it must be able to pass through steel, so the only rays, the only emission that can pass through steel is your gamma. Alright, because if you use beta or alpha particles, definitely it will be blocked already. The detector will not be able to detect anything except the background radiation. So definitely gamma. And now regarding the half-life of the nuclide, it has to be in terms of days, because you do not want all these radioactive substance to be present in the paint and you go and paint your house. If the half-life is very long, that means the resident that stays there will be exposed to all this radiation. So you do not want that. You want it to be as short as possible, but of course not that too short. So C will be the answer. Now, just to another application that's similar that you will choose a half-life to be short is where for medical use. Of course, all this radiation is harmful to the body, but if because of the diagnosis which is useful, so you consume them and the half-life that you choose has to be short so that you can do the test, you can diagnose, but then the radioactive substance will be gone within days or weeks. All right, you don't want it to be inside your body for a long time. In this question, you're asked which pair of properties is correct for the beta particles. Now, just recap: beta, which is an electrons, so 0 minus 1, and electrons is negative charge. All right, this is what we know. And beta, as mentioned, is in the middle, so it will be able to pass through the few mm of aluminium, air, or skin or whatever, but it will be blocked by a few mm of aluminium. So the answer is no, it cannot pass through 2 cm of aluminium. And so these two are wrong. Now, will it be deflected by electric field? Remember I said if the particle is charged, it will be deflected by the electric field. So by the laws of electrostatic, light charges repel, unlike charges attract. Now so the answer will be B, it will be deflected. Now just to revise, if this is a positive plate, this is a negative plate, you will have your electric field in this direction. And if an electron were to flow in here, electron is negative, so it will be attracted by the positive plate on top and repelled by the negative plate below. So once it enters into the electric field, it will be deflected upwards. And take note, once it's outside the electric field, you should know that you will go continue in a straight line. So another application is for, let's say you are making paper. So the thickness of the paper, you want to control it. So from the original, the raw material, you have to go through a roller to press it to the correct thickness that you want. And you will monitor the thickness by using all these the beta particles. So the question asks you why alpha particle is not used. So very straightforward. As mentioned, alpha particle will be absorbed by a few cm of air, your skin, or even a thin piece of paper. So this paper definitely will absorb the alpha particle. So the answer will be A. So for this question, okay, you're going to discover whether a radioactive source is emitting alpha particles. And let's recall, alpha particle is actually your helium nucleus 42, the least penetrating, and you'll be easily blocked by a few cm of air, thin paper, or your skin. So the person moves the paper between the source and detector, and there's no difference in the count rate. Let's go through all the options here. Let's look at A. The paper does not absorb alpha particles, which is wrong. It will be absorbed. Next, for B, the count rate due to the background radiation is too high. Now, this one is wrong. Why? Because if there's alpha particle with the paper, the count rate, it will absorb the alpha particle, so the count rate will definitely decrease regardless of what is the count rate for the background radiation. Now let's go to D. The source emits beta and alpha. Now even if it's true, if there's alpha and beta, with the piece of paper there, the alpha particle will be blocked, there will be a decrease in the count rate registered by the detector. So since it's given that there's no decrease, so D will not be the answer. So we only left with C, and obviously C is the answer because the radioactive source is too far from the detector. Now remember the basic. Alpha particle can be easily absorbed by a few cms of air. So this is placed 30 cm, so which is quite a big distance, so it will be absorbed by the air, so there's no difference in the count rate, or if there's a count rate, it's just purely background radiation, so there's no difference. Alright, for this question, the radioactive source is placed 3 cm from the GM tube. The average count rate is 742. So you have different materials placed between the source and the tube, and the results are recorded. That means to say, once you place the thin card, a piece of paper, in between the radioactive source and the detector, the value drops from 742 to 273. That means to say there's a presence of alpha particles. And next, when you put a aluminum foil, there's the value remains about the same, 275, 273. So that means to say there's no beta particles. But some students may say that but the value changed. But remember, radioactive decay is a random process. Okay, it doesn't mean that the count rate will stay fixed at a constant at that value. It actually fluctuates about a constant value. And lastly, when you put a thick lead, it's further reduced to 68. Okay, thick lead is able to absorb the gamma. So the 68 most probably will be your background radiation, by the way. So there is presence of your gamma rays. So the answer is alpha and gamma. So the answer is B. So for this last question, the application is using this radioactive emission to produce plastic sheet, and a radioactive isotope and detector are used to check the thickness of the sheet. Now, because it's a plastic sheet, you definitely cannot use your alpha particles because it will be easily absorbed by the plastic sheet. So your detector can't detect anything, so there's no way to tell whether it's too thick or too thin. So alpha, definitely wrong. You're only left with either C or D, beta. Okay, now maybe I explain a bit further. So if this is your beta radioactive source, and if there's no plastic sheet here, let's say this is the detector, just randomly give a number, let's say it's 500 counts per seconds. All right, so if the thickness is correct, of course before that there's a roller to press it to the correct thickness. If now there's a plastic sheet goes over, and some will be blocked, some will be absorbed, some can still pass through, and the value goes to, let's say, 300 counts per second. This 300 counts means the thickness is correct. What if due to some reason the thickness exceeds the requirement. So if it's thicker, more beta particles will be absorbed and the reading will be lower. Let's say 250 counts per second. If it's 250, so it will send a signal to the roller. Because it's too thick, now it will it will increase the pressure to press it harder so that the thickness will go back, and then the reading will actually be higher back to 300. Then that's the correct thickness and the production continues. Likewise, if the figure goes to, let's say, 400 counts per second, that will give you a hint that you're receiving more beta. That means it's too thin already. So what it does is it send a signal. It will reduce the pressure so that the thickness will go back to its requirement. So the reading will go back to 300. Okay, so that's how it works. So the next thing we need to know is actually about the half-life. Should it be a few minutes or several years? And for this application, you want it to be several years. So the answer is D. Why is it so? Because firstly, if the half-life is just so short, a few minutes, that means to say the radioactive source will decay too fast and you have to replace it, constantly replace it and calibrate the device. It's not so much of the count per second keep on dropping fast, because actually it's computerized. You can actually program it to actually cater to that. So it's more practical to have it half-life longer so that you can use it for a long time, and the counts per seconds for the correct thickness should more or less remains there. But of course it's not actual in the real world, as long as you're within that threshold. So let's say it's 290 counts per second to 310. So as long as the count rate is within this range, the thickness is correct. All right. So I hope this video give you an overview of how to solve question regarding penetrating powers of the emissions, and also what kind of application and what kind of emission is used. All right. Thank you.